So this kind of follows on a little bit from talking about when we talked about League of Legends in week 7, I think that was. The idea of player ranking systems. And this was by request, someone asked me to talk a bit more about different systems. And so this is a pretty high level approach, but it actually kind of relates a little bit to the central limit theorem. And so I figured it made some sense in week 12. So there are lots of different ranking systems within games, and two of the common ones are ELO and Glyco. So ELO works basically assuming that a player's performance on a game is normally distributed. And so if with the mean being your score, your ELO score. And so if you had two players that have the same score, then they both have the same normal distribution with the same mean. And so if they play each other, they would have each a 50% chance of winning a game against each other. So without loss of generality, right? If you have two random variables that have the exact same distribution, then the probability one is bigger than the other is 50%. If the scores are different though, so like if you had, here let me just kind of sketch out like two normal curves, like this is one player's score and this is another player's score, like that, so two different normal distributions. Of course it's possible for the worse player to beat the better player, it could happen. And the probability of the worst player upsetting the larger player is related to the difference in the means. So the difference between the means tells you how likely it is that the worst player will beat the better player at the game. And so just some benchmarks: if the difference in the scores is 100 points, then the player with the higher score has a 64% chance of winning, and the other player has a 36% chance of winning. If it's further apart, so if it's 200 points difference, then it's 76% chance for the higher player to win, and only, I guess, 24 for the lower player to win. So that's kind of how that works. And then every time you play a game, so you have a score, you have a score that only changes when you play a game. So when you play a game against someone, generally the winning player takes points from the losing player according to the expected outcome. So if a player that's much better beats a player that's much worse, that's not very surprising. So they might gain a very small number of points or maybe even stay the same. If it's an upset, so if a player that's worse beats a player that's better than them, then the worst player takes points from the better player. So it's kind of like a zero-sum kind of game. And of course, it's possible sometimes for draws to happen. And sometimes if like a bad player and a good player draw, the bad player might still gain some points from that because they were expected to lose, but they actually drew. So that's that kind of system. The Glyco system is a sort of similar idea to that, but it has an improvement in that the major issue with the ELO system is that your score is static. It only changes when you play another game against another person, and none of the characteristics of you or the other person you're playing against, other than the score, matters in terms of how much your scores change. So the Glyco system improves on that by basically incorporating the idea that your score is not a number, right? It's a mean of a distribution, and the variance of that distribution affects, and should affect, your probability of winning and then how your score changes. So it has something called the ratings deviation, or RD, which is basically just the variance, the standard deviation, so the square root of the variance of this normal distribution. So it's still assuming a normally distributed score, or ability, I guess. The mean is the mu, whatever, and then the ratings deviation is the sigma, the standard deviation. So then obviously we could think about a 95% kind of like confidence interval. You'll talk way more about these in Stat 231 when you get there. But the probability that their true score is between mu minus 1.96 sigma and mu plus 1.96 sigma is 95%. So obviously the smaller sigma is, the tighter that interval is. And generally the more games you play, the smaller your ratings deviation is going to get. So the more games you play, there's more certainty about where you are relative to other players and your skill level. And so that interval will get tighter and tighter and tighter as you have more experience. But a new player might have a score wherever it is, but it might have a very wide deviation because they just haven't played very many games. So we don't really know how skilled they are. So again, the Glyco system takes this into account when players play a game. Again, both the score is going to be adjusted up or down, but also the ratings deviation is adjusted. So as you get more information, generally your deviation goes down. And the amount that the players' scores are adjusted also depends not only on the difference between scores, but on the deviations of the two players. So if you have a very low ratings deviation, which means it's pretty sure you are where you are and you're in the right place, your score is correct, and then you lose or win, your score is not going to change as much as if you had a wide deviation. And similarly, if you are playing against someone that has a really wide deviation, then basically it's saying like, we don't really know anything about this person, so your score is not going to change by as much as if, two players with very narrow deviations played each other. So that kind of, again, incorporates the additional information of the uncertainty level of the score, and your uncertainty is going to go down, so like the accuracy is going to go up as you play more and more games. But it also kind of degrades over time. So if you go a long time without playing any games, then the uncertainty kind of swells back up a little bit because, maybe you got worse. If you stopped playing chess for a year, you probably would be worse at it when you came back to it. So the deviation is pretty sophisticated in that it takes into account how long it's been since your last rated game, and as well as how long you've been playing overall. So I will post some links to honestly, the Wikipedia pages are a great place to start for both of these systems if you're interested in learning more, but they do have to do with this idea of the normal distribution and the variance and standard deviation. So think about why this matters in sort of the longer term. If you're playing someone that has a lower score than you, either ELO or GLICO, any kind of score, if you play them in a single game, of course there's a possibility that they will beat you. Even if you're much better than them, there's a possibility that they'll get lucky. But if you play them over and over again, like under the same conditions, then eventually the law of large numbers is going to take over, and the proportion of games that you win will approach that true probability of you winning. So that's, again, kind of related to the law of large numbers, a little bit to the central limit theorem, the idea that as we have more and more samples of a thing, then the distribution is going to approach the true theoretical distribution of that outcome. Alrighty, so not a lot of technical stuff in today's game thing. But if anyone has any questions about that, please feel free to ask. Oh, I see someone else. Hello on Piazza. Okay. Well, then I think I'm going to move on and talk about the machine learning idea of the week. I don't have like a piece of paper or whatever, a document for it. I'm going to be referring to this really, really great resource called this book known as I can't write. Sorry. It's called Weapons of Math Destruction. It is a fabulous, eye-opening, earth-shattering book. I just love it so much. I got to meet the author, and she signed my copy of the book when she gave a talk in Waterloo a couple of years ago. But it's a fascinating book, and I just wanted to kind of touch on some of the ideas because they all relate to this idea of what machine learning algorithms can do and what good they can do and also what harm they can do if they're not understood properly. So any kind of machine learning algorithm, we talked about this in week 6, I think, it's going to require data, good data, to give good outcomes. So if you give it biased data that doesn't represent the sample population that you're trying to model, then the results are going to be garbage. They're not going to be good at predicting what you want it to predict if you don't have accurate data going in. But the danger comes when a machine learning algorithm takes in data that is maybe accurate and then uses it and then repurposes or sort of reproduces the same results that went into it. That's where the danger happens. Instead of kind of being self-correcting, it can create feedback loops that end up harming more people or disadvantaging or giving worse results overall than before the algorithm was even employed. So I want to just talk about a few different examples. One of them, let's imagine you're a university and you want people to come to your university, like as universities do. There are these rankings. There's lots of different systems for it, and they all sort of rank universities on various criteria. In Canada, there's the Maclean's rankings, but there's lots of international ones as well. They rate different programs or different universities as a whole. And how you do on those rankings is pretty important, actually. Like, a lot of people pay attention to that. The criteria for what the rankings are looking at is usually fairly transparent, which is a good thing generally in an algorithm. You want it to be transparent about what you need to do well. But the issue is that the things that make you have a high ranking are not necessarily the same things that make a high quality experience. And so it ends up sort of reinforcing the fact that, I can't think of a specific example, but certain, spending on sports or something, if that's one of the categories in the rankings, and universities decide, oh, we want to move up the rankings, so we're going to put more money into that. That sort of, is that really improving things for everybody? Maybe not. Another thing is that things in the ranking, one of the things in the ranking is like the amount of alumni donations. And obviously older, more established universities have more alumni and richer alumni. And so they end up sort of getting more and more funding. And then that sort of reinforces their position at the top of the rankings. So it can end up being like a feedback loop of where a new, younger university can't actually move up very quickly because they don't have access to like the criteria that they need. So again, just like putting money into things where it doesn't necessarily need to be just to move up in the ranking is an unintended consequence of making those rankings so transparent about what goes into them. Another example might be something like looking at credit score for insurance. So this is something that happened in the United States and in Canada to some extent as well, probably other countries too. This is like an actuarial example, which is my background. So some actuaries discovered that it turned out that people who had higher credit scores, so generally like less debt or less credit card debt anyway, fewer bankruptcies, fewer defaulted accounts, and fewer declined transactions, that kind of thing, more history of paying bills on time, et cetera, also had less car accidents, fewer car accidents. And they were like, oh, cool, well, that's great. We can get access to people's credit scores and then use that to help price their car insurance. So if someone has a high credit score, they might get a discount on their car insurance. And that's kind of weird, right? Like credit score as a thing, to determine someone's creditworthiness makes perfect sense. Right? It's an example of a good kind of algorithm where the thing that you do to fix your credit score actually does improve and demonstrate that you have improved credit. Unlike the university rankings that aren't necessarily related, credit score is usually pretty good in practice at saying, okay, like if you want a higher credit score, then pay your bills on time and don't open new accounts and then run out your credit card. So generally, it's the kind of thing where the behavior that it tries to encourage does reflect the behavior that they want to incentivize. But the problem comes when you then use that credit score to do something other than assess creditworthiness. Just because someone pays their bills on time has no implication as to whether they would be a good driver or not. And what ended up happening is that by using credit score as a proxy for some factor that they were trying to capture, all it ended up doing was basically punishing people that were poorer. Because people who have higher credit score generally haven't had to struggle to pay their bills. They have high credit scores because they have money. So it just ended up charging more money to people who could least afford to pay it. And that's obviously not a good thing. So making sure that if you're using some data into an algorithm, that it actually is appropriate for the purpose. Like just because it's correlated with something doesn't mean it's appropriate to use. It doesn't mean it has a causal relationship at all. There's a just absurd example of two people in the same area. One of them had a previous drunk driving conviction, but a high credit score, and the other one had no traffic tickets, but a low credit score, and the person with the low credit score was paying more than the person with obviously a worse driving history. So things can get out of hand when you use something that's maybe unintentionally a proxy for just wealth or other factors that shouldn't be related to their driving abilities. One last example I'm gonna talk about in like a situation that could happen. Imagine that, oh, I see a question, sorry, let's do that. What are some of the parameters used to determine whether the data is relevant to the algorithm being tested? That is such a good question. And if I had the answer to that, it would be great. I don't think anyone has like a magical answer, but it's super important to go through that process. So, if you're working at a company that's, doing predictive stuff, like just even like, Amazon predicting what people are going to buy, or like Target had a really good thing where they were trying to predict whether their customers were going to become pregnant soon so that they could send them coupons for baby stuff. But yeah, how to determine what is appropriate to use is such a fraught issue, right? Obviously, like, at the very least, it should be something that's legal to collect, right? You can't just, like, go spying in people's garbage, or, like, something legal to collect. Ideally, something that's in the person's control. So, you know, something like, I'm just trying to think of a good example and a bad example. So something that they can actually change. So, like, you know, if your height or something, like, you can't change your height. Like, so you shouldn't charge different amounts of money for somebody based on height, because they can't really change that. Race as well. You shouldn't be, like, charging different people things based on something they can't change. Actually, gender as well. So, like, some places don't allow car insurance or any type of insurance to differentiate based on the gender of the person. Some places do. So I think in Ontario, my husband and I pay different amounts for our car insurance because we're different genders. But like, in some places you can't do that. In some places it's illegal to use certain factors. So that's the bare minimum, is it must be legal. But also just interrogating, is this actually what we want to be measuring? Is this actually causally related, ideally causally related, not just correlated with what we're trying to model? Again, such a good question, and there's no magic way to tell whether something is good or bad. It's all kind of shades of gray, but maybe having multiple people look at it from different lenses would be another good thing. So if one person looks at this and says, oh yeah, that's totally fine, we can use that, someone else might notice something about it, like, oh, actually this is really correlated with neighborhood, and neighborhoods are really correlated with other socioeconomic factors. And so it might end up, you know, disadvantaging and charging people more than they should be paying just because of where they live. And not in a way that actually correlates with their actual risk. So again, I'm sort of mostly talking about, like, insurance applications here, but it applies for everything. Even just, like, ads, like who to show ads to. Like, job ads or something on LinkedIn will pop up for different people. And if you tell the algorithm, okay, find me people who we think are going to be interested in this job, and they do that by giving them a list of people who have had the job in the past, then obviously the algorithm is going to just show the ad to people similar to the people who have had the job in the past. So it's not going to be good at getting new, different folks involved and like interested in applying in these kinds of jobs. So that's kind of an example of maybe some things you can do to check whether something is a good idea or a poor idea to include. So legal, something the person can control in some way, maybe. Causally related, not just correlated, and have lots of different people look at it and see it from different lenses to see whether it's a good or bad thing to include. Thanks for the question. So this next example that I was going to say actually ties in very, very closely to that idea. So imagine that you are Waterloo Region Police Service and you want to cut down on crime in the Waterloo region. It's not that high to begin with, but just let's say that's your job. So what you do is you say, okay, let's put into this algorithm all of the violent crime data that we have from all of Waterloo region. Well, there isn't very much of it, so it's not going to be a very good predictive model. There's not a lot of it, and so it might tell you something, but it might not tell you very much. So then you say, okay, well, let's just add more data in. Let's take all of the data from all of the crimes we have, including like nuisance crimes like loitering or, you know, public urination or whatever, like crimes that aren't as serious. And so if you put all of that data in, especially things like noise violations, noise bylaws, and loitering, what's going to happen is it's probably going to say that the student areas have more crime because those types of nuisance, like not really super harmful crimes, tend to happen in the student areas. And so the algorithm is going to say, oh, whoa, we have way more crime happening in the student areas. We better send more officers to the student areas. And then they'll do that. They'll say, okay, the algorithm told me to go here. Here I am. What's happening? They look around. Oh, there's somebody doing something. So it'll end up causing over-policing of certain areas. And then what's going to happen is the algorithm is going to loop back on itself. All of that new data of all of these nuisance crimes is going to go back into the system and say, whoa, we caught way more crime in student areas. Well, of course you did. You sent the officers there. And so it'll say, okay, great, we got to send even more people there. And it's a feedback loop that ends up in over-policing of certain areas. And so it ends up inflating the amount of crime and then looking like it's justified by this impartial algorithm. But it's not impartial because it was, seeded with this biased information. It ended up reinforcing the inequality and the over-policing of certain areas. And it sounds kind of like a silly example, but this exact thing happened in lots of cities where they have kind of predictive policing algorithms. And it ended up basically telling the officers, okay, if we include these crimes, we'll send more officers to these areas. And they tended to be disproportionately racialized neighborhoods. And so those neighborhoods were over-policed, and that was then sending more data back into the system justifying this behavior. And that led to just absurd amounts of over-policing of racialized neighborhoods, and just a complete inequality that is still bad. So again, that's an example of an algorithm that seemed to be impartial, but because it was sort of seeded with some biased data and ended up reinforcing that, it ended up in a not so great situation in the end. So that's another example of like making sure that you want to include the data that you actually want to include and not just reinforcing the existing inequalities. So those are sort of 3 examples. This book is amazing, and it has hundreds more. Fascinating book. And again, it doesn't really have any answers as to how to fix this problem, but definitely looking at things like just, again, interrogating whether the data that you're using is actually doing the thing that it wants to do. Is the data biased? An algorithm itself is not impartial. It's based on whatever data is put into it. And so you can't trust an algorithm itself to have a sense of, moral authority or anything. It's just numbers and just what it's worth with what it's given. So unless you deliberately focus on making your algorithms fair, the bias might creep in. It might be very insidious, you might not notice, but it might be there, and it could have devastating consequences. So that's my sort of machine learning idea of the week. Definitely check out this book. The author is Kathy O'Neill. I hope I spelled this right. Oops, that's an N. I might have 2 L's. I feel terrible if I got that wrong. But she also has a TED Talk, and just fascinating, all of this stuff that can go wrong if algorithms are not well understood. They can be wonderful, and they can be great, and they can do amazing things if they're understood, and if they're specifically having the right purpose and the right types of outcomes. But they can be devastating if they're not following those instructions. Okay, so that is everything for my machine learning idea of the week. Happy to take any questions on that. And then I wanted to quickly do a little demo of the central limit theorem in R. Story time. When I took Stat 230 1,000 years ago, I did not believe the central limit theorem. The instructor said, we're not going to prove it. And I said, why not? And they said, that's beyond the scope of this course. And the proof is in the course notes now, but it wasn't back then. There was no proof provided in the course notes. And me, being a giant nerd, said, no, I refuse to believe it unless you prove it. So I went an entire year not believing the central limit theorem. And let me tell you, it's not great to be a stats major and not believe the central limit theorem. Eventually, when I took Stat 330, we did prove it, and then I believed it, and boy, did I feel stupid. But it just didn't make sense to me. How can you say, essentially what the central limit theorem says is that if you take a bunch of random variables, any random variables at all, and add them up, you get a normal distribution. And that did not make sense to me. Like, how can you take a bunch of, say, like geometrics, which are like super skewed? How can you tell me that if you add up enough geometrics, you get a normal looking distribution? It just did not make sense to me. So what I wanted to do is like prove it to myself, kind of not with math, which is a bit, again, the proof is a bit over technical, but it is in the notes if you really care. I wanted to sort of demonstrate it with R. So imagine that we're going to just start by rolling a fair 6-sided die. So I'm going to just roll, I'm going to take a uniform on 1, 7, and then chop off the decimal. That'll give me a uniform 1, 6 discrete. And down here, I think you can see them. Yeah, we can see that we have, here we go, 10 rolls of a fair 6-sided die. So we got a 6, 2, 5, 1, 6, 1, 4, 3, 4, 4. Cool, great. Let's do that. That was 10 times. Let's do it 10,000 times. I'll do that, and then I'll graph it. So here we go. We have got the histogram of these. I'll put it down here now. Don't need that. Pardon me. A histogram of these rolls of a die, and you can see they're not perfectly uniform, but it's pretty close. We see have a few more 6s and 5s and 3s and a few less 1s, 2s, and 4s, but basically it looks pretty uniform. So that's pretty neat. What if we though take two dice and roll them? So I'm going to do the same thing. I'm going to just set myself up a blank vector here, and then take 2 uniform random variables here and add them up. So that's what I'm doing here. I'm just filling in each spot in this vector with a distribution like that. And then if we want to plot that, we see it looks like this. So that's, again, what we expect, right? 7 is the most common, 2 and 12 are the least common. This is the distribution that they have, of course. You know, if you play Settlers, you can, that's 6 and 8 are the best places to put your guys, that kind of thing. So that's what we expect. Again, this is the sum of 2 dice rolled 10,000 times. Well, let's keep doing it. Let's try summing up 3, 4, 5, 10, a few different numbers of dice. Let's go 3, 4, and 10. And I'm going to plot them and see what they look like. So in R, this is how to show multiple plots at a time. Par MF row equals C15. That's going to make a 5 side-by-side plots. You don't need to use that ever, but in case anyone was curious, that's how you can do it. So I'm going to plot this once at a time. So here we go. That's the sort of uniform distribution. This looks kind of weird. I'm gonna shrink this a little bit. There we go. That looks better. Okay, and this is 2 uniforms. We have this distribution that looks like this. 3 uniforms looks like that. Ooh, okay. 4 looks like that. And 10 looks like that. When we get to 10 here, if you look at this histogram, it looks pretty darn close to a normal distribution when all we were doing was adding up uniform distributions. You add up 10 uniform random variables, and the histogram ends up looking very, very close to a normal distribution. And it turns out that that's, you know, you can do a pretty good approximation of the sum of 10 6-sided dice with a normal distribution with the mean equal to 35, which is 10 times 3.5, the mean on a single 6-sided die, and variance equal to whatever the variance of a uniform 0.6 is times 10. I can't remember the formula off the top of my head. So pretty neat. We end up with this bell curve looking thing just by adding up independent uniform 1/6 random variables. All right, so that's cool and all, but like we started off with a distribution that was flat, which was like symmetric. You know, yeah, it was like, you know, fixed finite range, but at least it was symmetric to begin with. And so adding up a bunch of those, it's not that surprising that we end up getting like a normal distribution, because you're like ending up with more in the middle and less on the extreme edges. What if we start with a super skewed distribution? So one that's like extremely light or heavy-tailed on one side and light-tailed on the other. Something like the exponential distribution or the geometric. Actually, both of those would work. So we're going to see the same kind of thing here. I'm going to make a bunch of exponential distributions here, just set up some blank vectors and add up a bunch of exponentials in each one. And then I'm going to show what the graphs look like for this. So if we start off with a single exponential density, it looks like that, right? Extremely skewed. It's like a huge point at the beginning and then off to basically nothingness. That tail goes on infinitely far. But this looks nothing at all like a normal distribution. Well, what if we have 2 exponentials? If we add up 2 exponentials, we get a distribution like this. Okay, like still very skewed. Definitely not anything symmetric or anything like that. What about 5? Oh, sorry, that wasn't 2. Sorry, that was already 5. So this is 5 exponentials. What about 10? 10 exponentials looks like that. 50 exponentials looks like that. And 100 exponentials is basically indistinguishable from a normal distribution. Isn't that crazy? So it's like taking these extremely skewed distributions and adding up a whole bunch of them, we end up getting something that looks basically indistinguishable from a normal distribution. Isn't that neat? And the thing I want you to notice though is here, it took a lot longer for it to look normal. Remember when we had the uniform 1/6, after 10, it looked pretty much normal. But 10 exponentials is this third plot in the middle here, this one here. I don't know if you can see my mouse. The one in the middle is definitely still skewed. It's definitely not a normal distribution at that point. So it took longer. It took up to 100 exponentials for it to really start looking like a normal distribution. And that's because we started off with a distribution that was so different from normal. So when we think about the central limit theorem, we always say like a higher n is better. The more variables you're adding up, the better. The better the approximation is going to be. But the n isn't the only thing that matters. The shape of the initial distribution also has an influence. If you start off with an initial distribution that's relatively symmetric to start with, then it's going to converge to something that looks normal faster than if you start off with something extremely skewed like this exponential here. So both the number of variables that you add up and the shape of the initial distribution will influence how quickly the central limit theorem is a reasonably good approximation. Someone on Twitch here said, normal distribution, I am inevitable. Yes, absolutely. Everything becomes normal. Again, there's some assumptions that go behind it, though. Here we were assuming independence. If it's not independent, the central limit theorem doesn't hold necessarily. And we also have the same mean and same variance, and both those means and variances are finite. So if you had a distribution that was had an infinite mean or an infinite variance, they exist. We don't have them in this course, but they do exist. Then the central limit theorem doesn't necessarily work the same way. But if we have any distributions where we've got independent, same mean, same variance, we add up a bunch of them, the result looks normal. Sometimes you might have to wait longer, sometimes you might get it pretty quick, but we do see this even when we start with a very skewed distribution. So hopefully that visualization was a little bit helpful, and you won't need to spend a year not believing the central limit theorem like I did. Again, let me know if you have any questions about that. If you want me to, I'm going to post all this code on Learn so you can play around with it yourself. But we end up with these cool, normal-looking things after just adding up a bunch of exponentials or before adding up a bunch of uniforms. And don't forget, there will be a final assessment review session next Friday, but not at this time. It'll be from 9 to 11 p.m. Eastern Daylight Time. So that was the vote. That came back as the preferred time for everybody, so that's when it will be. Oh, will that be recorded? Yes, it will. Yes, thank you for asking. Yeah, so it'll be, if you can't make it during the time, then yes, you'll be able to see it later. But I do encourage you to come because the session is just like the midterm review session. It'll be completely driven by your questions. I'm not going to have anything prepared that I'm going to tell you about. It'll just be based on what you asked me to do. And so if you have anything, could be literally anything from one of the sample finals, either the one in the notes or the one that's posted, any of the Mobius questions you've had all term, anything from the midterm, anything from the assignments, anything from the course notes or videos or problems that you found anywhere else. Happy to answer questions as long as you keep asking them until 11 o'clock. Then I'll stop because I want to go to bed. And yes, I will record it, and I'll do the same thing as usual, kind of edit out the dead air in between questions and upload it to Learn and also to the YouTube playlist. Oh, how would I find the range of a normal distribution? Okay, so a normal distribution is the entire real line. Done. That's the range. You might be thinking of the range of the PDF of a normal distribution, which is never asked for. But if you need it for something, you know what the PDF of the normal distribution is, and you know that the PDF is maximized at the mean. So you could plug in like x equals mu, and then the e to the negative 1/2 blah, blah, blah will just disappear. So 1 over root 2 pi sigma will be the maximum value, but that's never asked for. The range of a random variable is the range of the random variable. It's not the range of the PDF of the random variable. So I think that might have been a few people who were asking that. And I think they were just confused by what range means. So remember that a random variable is a function that maps points in a sample space to real numbers. So the range of the random variable, like the domain of a random variable is the sample space. The range of the random variable is the values it can take on. And then if you think about like the PDF, okay, the domain of the PDF is the same as the range of the random variable. And the range of the PDF is whatever it is, depending on the distribution. So for a normal, it's always got to be above 0 because PDF can't be negative. Variables can be negative, but PDFs can't. And then the maximum is some value. Again, in the case of a normal, it's maximized at the boop, like the top of the curve. That's the official term, the boop of the distribution. No, it's maximized at the mean, where that curve peaks. And that, of course, is going to be 1 over root 2 pi sigma. Oh, I have a funny story. I was talking to someone during office hours, and my son was hanging out in the room. He's 8 years old, and he heard me say 1 over root 2 pi sigma to the student, and he goes, "Mommy, why did you say 2 pi? Why don't you just say tau?" And I was like, my son is a math nerd. I'm so proud. But yes, 1 over root tau, if you prefer, sigma, or 1 over root 2 pi sigma. And the videos from this week, if you haven't had a look at them yet, there are, I think, 3 or maybe 4, mostly about the central limit theorem. So this video hopefully will make that a little bit clearer why that works. If you just add up a bunch of normals, you end up seeing, if you add up a bunch of any distribution, you end up getting a normal looking thing. And then that can be used as an approximation under certain conditions. And then there's also a video about moment generating functions, which is an interesting topic. Moment generating functions is another tool that you can use to answer problems. It's a quick way to find means and variances of distributions. It's also a really quick way to prove relationships between random variables. So like the fact that if you take a bunch of independent Bernoulli random variables or indicator random variables with just probability p for success and 1 minus p for failure, and that are independent, if you add those up, you get a binomial distribution. And that's easy to prove, trivial to prove with moment generating functions. Similarly, if you add up a bunch of independent geometric random variables, you get a negative binomial. And that's hard to prove with the probability function directly, but it's easy to prove with moment generating functions. There's something that's come up a few times on Piazza is for question 2 of the third computer assisted assignment. There's 2 ways that you could do part E, which is the sort of the simulation to confirm your calculations earlier. The way that we expected you to do it, and that's sort of like hinted at in the question, is to just use the theoretical probabilities from part A. So in part A, you would find the probability of 2 trucks, 3 trucks, 5 trucks, or anything else lumped together. So there's like 4 possibilities. So you could just use those 4 probabilities and simulate from a multinomial distribution with those probabilities. But you could also, instead of doing that, you could also just simulate from a Poisson distribution how many trucks there actually were on each of the 7 days in a week, and then somehow count up how many of them have 2, 3, 5, and other. So you'd have to simulate more variables that way because you have to simulate like 7 variables for each line. But that's a perfectly fine way of doing it if you want to do it that way. We have told the TAs to accept either answer when they're marking, so whichever way you want to do it is fine. I also had a couple of questions. I saw a couple of times people asking about using like R to answer those theoretical questions. And so you shouldn't need R or any kind of software or anything to be able to do those theoretical questions. If you do, maybe you're overthinking it. So you can, of course, like it's perfectly fine if you want to use like Wolfram Alpha or something like that to verify the calculation, but you should not need it. And so if you are finding that you need a really heavy calculation tool, then you might be overthinking the question. So if you're not sure, have a look at what's going on the discussion board. Lots of people have been giving perfectly legal hints to each other. And so that's you shouldn't need too much super heavy calculation. Well, have a great weekend, everyone. Good luck finishing up your last computer assistant assignment and your last quiz. So quiz 6 will be available until next Wednesday at midnight, which is also the last day of classes. Please don't forget to fill in the course evaluations. Those are still available at evaluate.urlu.ca until the same time as the deadline for quiz 6, until 11:59 p.m. on Wednesday, April 14th. We'll have our final assessment review session next Friday, 9 to 11 p.m. And then your final assessment is on Tuesday, April 20th to Wednesday, April 21st from 4 p.m. to 4 p.m. on both days. And it will be, as discussed, 2 parts. One part is 15 Mobius questions. The other part is probably 5 long answer kind of crowd marky questions that will be delivered to you through Mobius. So best of luck, everyone. Have a great weekend. Good luck finishing up everything for all the other classes. There's no new material or anything next week. It's just wrapping up everything from this week. And see you at the review session.